Good morning, everybody. Is it working? Can you hear me? Can you see me? Is it okay, just like yesterday? Are we good?
Yeah, good.
Yeah, okay, perfect. Thank you. Okay, so that's our second session together. We're going to move on. We're going to build on what we started to see yesterday. Yesterday was more introductory. And I'm going to start today by finishing yesterday's first lecture before moving on to the next one, because I think it's better that I cover this right now. So let me share my screen. So everything is recorded like yesterday. If you go and check the Google Drive, you will find the slides for today's lecture, as well as some materials for yesterday. And then there is also a Word file. And if you open it, then you will find the links to the various recordings. So for now, there is one recording. And then once this lecture is over, then I will add the next recording tonight here, and so on and so on. So you can check the recordings later on. Or if some of your friends join a bit later in the morning. So let me finish first what we started yesterday. So I'm going to share my screen. All right, and I should share with you this one. Okay, so I'm going to put the chat here so that I can see everything. All right. And if you don't mind muting your microphone, then for sure we don't have the background noise from time to time. Makes it a bit easier. So what I want to do before moving to the second session, the second lecture rather, I want to introduce deep learning and natural language processing, broadly speaking, so that you get an idea how I will come back to it later on. So the first thing is that there are two areas when it comes to deep learning. There are two areas which have seen the most progress. One area is called computer vision, and the other area is natural language processing. So this is where the impact of the new deep learning approaches, this impact has been the strongest. And if you would go to the conferences related to natural language processing, you would see that at these conferences, these academic conferences, the number of papers which rely on deep learning keeps increasing. So that's what you can see with the small graph on the slide. Back in 2012, for ACL, for instance, so the largest, I think the largest conference in NLP organized by the Association for Computational Linguistics, maybe around 40% of the papers were related to deep learning. And today, I guess, is around 80%. So that gives you an idea of how deep learning has become the dominant approach in natural language processing. So that's the first thing to emphasize. Then what I would also want to tell you is that when you think of computer vision, so the way we can, or the computer can perceive visual scenes, and when it comes to processing language, there are in a way some connections between the two. And that means you will see that concretely there are some techniques which can be used for computer vision, which can be translated to language, natural language processing. And the idea is a little bit like this one. When you look at you look at a visual scene, let's say you look at a picture, you will detect a number of small elements, small parts, some small components of this picture. And these components can be assembled into slightly larger components. So you start from these small components with their edges, their patterns, their colors, and then they can become part of larger components. And you can, in a way, integrate in a hierarchical manner the visual scene. So you can go from the smaller components to the whole picture. So that's something, that's how our brain, our mind will process actually visual scenes by looking at all the smaller components and assembling them into something larger. It's not the only way, but that's in good part how it works. But now if you think of sentences, something like a small crowd quietly enters the historic church. What you can see is that you also have in language this hierarchical structure. That's what linguists have been knowing for a long time. You can group, for instance, historic and church, because the adjective is connected to the noun. So you have this group, which what we call in linguistics a noun phrase, NP. That's one slightly larger component made of two words. And then if you add the, then you get something larger. And then you will integrate this with the verb, and then you will have the verbal phrase. So that will be this one. And then the subject and the verb phrase together, they will create the sentence. So I think what you can clearly see with these two illustrations is that this hierarchical integration is shared both by the parsing of natural, by images, visual scenes, and the parsing of sentences. That means there is one difference, which is the number of dimensions. When you process a picture, an image, you have two dimensions. When you process language, I'm going to repeat that in a moment, you rather have one dimension. But some of the techniques used for two-dimensional images, actually you can translate them rather well to one-dimensional language. Something like convolutional layers. I'm going to explain that in a few seconds. So that's something I want you to have in mind, this kind of analogy between vision and language, to some extent, at least. Something also that maybe makes very good sense if you have played a little bit with deep learning and if you do machine learning is that neural networks, they only accept one kind of inputs in a way. They only accept numbers, possibly lots of them, but only numbers. And usually you try to choose rather small numbers. So like numbers between -1 and 1 or 0 and 1. That's quite common because large numbers may create some issues when you train the network. So that's what you will give, you will feed deep neural networks. But languages, sentences, they are made of words, which means that first, if you have words and sentences, you must transform them into numbers in order to feed them to the deep neural network. So what kind of inputs may we consider here? There are different things you may think of. You may think of speech, therefore something like sound waves, like the numbers which can describe sounds, what you will have in an MP3 file or a WAV file, for instance. And you could kind of encode acoustic information with numbers. You may also think that words rather than sounds are more adapted to what you want to do, or sentences. These words, you might also turn them into numbers. Or maybe you want to focus on letters instead and other symbols, written symbols like punctuation marks, like comma and dots and two dots, semicolons, these kind of things, and spaces and digits also. You may encode all these elements as numbers so that once again, you can feed them to the neural network. Neural networks, they kind of don't care. They do not expect something when it comes to their input, the format of these inputs. They are in a way agnostic. But in practice, depending on what you want to achieve, some formats will work better than others, or will reduce the amount of training necessary, or something like that. So that's something you need to do. I'm going to skip these two because I'll come back to it later on. But people, of course, they have been trying to find the right strategies to encode numbers or words in particular into numbers. And there is something well known, which is called one-hot encoding. Basically, it's one and then only zeros. That's how you may encode the words. And today we have something better because one-hot encoding, it works, but it's not the best approach. Now we have what we call word embedding. And the idea is that you represent words with vectors of numbers. And actually, these vectors of numbers, they encode the meaning of the words. Not perfectly, but not so badly either. So I won't spend time here because I'll come back to it later on in the next lecture. So you need to encode your words or your letters or yet something else into numbers. Something else that is very important when you consider language is that it's different from an image. The point is that when you think of language, language is like unfolds along, like through time, along one direction, the dimension of time. So maybe you could say that language is not two-dimensional, is rather unidimensional or unidirectional. What I mean by that, okay, sorry, I see a question. Why one-hot encoding is not good? It's not good because it's too sparse and the words are kind of disconnected from each other. So with one-hot encoding, you cannot encode semantics, the meaning of words at all. When you do word embedding, you get better, something better. But I'll come back to that later on. So it's just one question to keep for in this like 3 or 4 days from now. So I'll come back to that. So if I come back to what I was saying, the words, they come one after the other. They unfold, right? The language unfolds. You say something and then it quickly disappears, one word after the other, one sound after the other, and then one sentence after the other. So when you create deep neural networks as systems to process language, you need to be able to deal with this unidirectional nature. What we do in our mind, and that's well known, is that we store early information, let's say the beginning of the sentence, for instance, to then integrate it with later information, the second part of the sentence. And we do that because in our mind, we have something that is very well known, which is called the working memory. And that's how we store information for a short time in order to integrate this information. So it's different from the long-term memory where you will have your memories, your what you did yesterday or stuff you did when you were a child and that you can still remember to some extent. This is the long-term memory. But then we have this shorter-term memory, the working memory. And that's how we can keep some words simultaneously together in our mind so that we can assemble the sentences and make sense of them. That's how it works in human beings. Now the question is, how do we do that with computers? When you do computer vision, there is something very well known and is not, I mean, it has been invented already some years ago. It is what we call convolutional layers. That's the most basic mechanism for deep learning of visual scenes. So very widely used. And when you have a deep convolutional neural network, that's a deep neural network consisting of a number of convolutional layers. And these layers, they are not like the fully connected layers, which are like the most common classical layers. These layers, they are connected to other layers in a way that they can extract patterns from their input. And it doesn't matter where these patterns are located in the input space. So let's say that if you have you are doing computer vision and you have let's say you want the network to detect car plates because you want to regulate traffic or something like that. If you use a convolutional network, you could have some neurons which become sensitive to car plates wherever these car plates, they appear in the picture. Bottom left corner, upper right corner, etc., etc. So we call this space invariant or shift invariant artificial neural networks. That's the term you may find. So if you have more and more convolutional layers, initially the patterns are more, I mean, are quite concrete. They are like small parts of the initial picture. This is what you can see on the right. You could have here this neuron here in the convolutional layer that specializes in detecting these small parts, like this angle. And then as you add more and more and more layers, the patterns that the later layers will be able to detect will get more and more abstract and more generic. Until in the last layers, you can kind of detect whole numbers or car plates or faces or yet something else. And then you can add a final layer, like a fully connected one. And then you can add an output layer and try to perform a given task. So you move from groups of pixels to components of an object to whole objects. That's what you can do with convolutional layers when it comes to computer vision. That's a 2D problem, a two-dimensional problem, because you have X and Y, the width and the height of the picture. And you might also have a depth if you consider different colors as well. That's also possible. And if you want to consider videos, then you will have 4 dimensions. That's what people will do. Colored videos, 4 dimensions. But let's keep it simple with only 2 dimensions. So these convolutional layers, the first one that were invented, in a way, they are 2-dimensional. But actually, it is totally okay to think of 1-dimensional layers. This is just a simplification, actually, of the 2-dimensional layers. And when you have 1D layer, then these layers, they are well adapted, suited to the unidirectional nature of language. So let's say that you could have a layer, 1D layer, and initially some neurons, they will become sensitive to small patterns, like the dog, the 2 words together. And it doesn't matter where these 2 words, they appear next to each other in the text. So we have this translation invariant. So this 1-dimensional convolutional layer, it will be able to recognize something like the dog and other patterns in different places. And then as you add more and more 1D convolutional layers, you will be able to detect larger and larger patterns. So these 1D convolutional layers and the corresponding neural networks, you may use them for some tasks in deep learning and NLP. Okay, there is a question from Jean-Claude from the previous one. I think here what you can see is a 2, right? So like here, this network, it would do a classification task. You provide a handwritten digit, and the output is that you have all these outputs, and you will get values for each neuron in the output layer between 0 and 1. And you will basically pick up the one with the highest activation, the highest value. So here, maybe if you have 0 to 9, if you enter 2, then after the processing, the neuron with the highest activation should be this one. Okay, so that's the 10 digits, 0, 1, 2, 3, 4, 5, up to 9. Does that make sense, Jean-Claude?
Yes.
So it's to detect the digits. Okay, good.
Yes. Okay.
Very classical, like toy neural network that when you learn deep learning, you will create something like that. But you can do it with language as well. The other thing that is very, very common when you process language, but I will tell you again about this later on, is that rather than having only feed-forward networks where the information is only moved from one layer to the next, we also have what we call recurrent neural network. Recurrent neural networks, they have inside them a number of recurrent neural layers. And these layers, basically, they have some sort of an internal memory, a little bit like the working memory in human beings. And it can integrate information over time. So if you check on the right, you will have information coming from the input layer. So it will connect to the different neurons here in the hidden layer, the recurrent hidden layer. And then this information, it will move to the next layer, but it will also go all right, it will also go to some other nodes, hidden nodes, which are called context nodes. And these nodes, they will again send information to the three neurons in yellow. So here you have created some sort of a loop. And then when you train the network, you set the weights of all the connections. This network will be able to process things which unfolds through time like language. So that's very powerful. It's not very easy and simple to train, but that's something you do a lot when you do natural language processing. Although today people start to think that you may actually do well, very well actually without recurrent layers, but I mean, that has been used for a long time and it works pretty well. I'll tell you more about this later on as well. So if you would check the progress, in 2003, we started to have some simple neural language models. And then in 2013, we started to have word embeddings, the stuff I've mentioned earlier on. And that was a leap forward. And then we started to have other things. And in 2014, we started to have sequence-to-sequence learning. So something like sentence-to-sentence learning, for instance. And in 2015, people invented what we call attention and attention mechanisms. And that was also something very important. And some years ago, maybe 3-4 years ago, then we started to have pre-trained models. And these are huge models which are trained by others and that you can use and you can fine-tune, which you can adapt to your task. I will tell you also about these models later on. This is really like what is most commonly used today. And you can do quite amazing things with these new models. So it moves pretty fast, okay? The field is changing quite fast. So that's what I wanted to tell you. Once again, is the unidirectional nature of language. It unfolds through time. We need to encode words or letters or sounds. We need to turn them into numbers. And then we have these convolutional layers or these recurrent layers to try to process these linguistic inputs. Of course, now that's really like the broad picture. Later on, I will tell you more. I will give you more details about this. So that's what I wanted to finish first today. Kind of give an example of a good word embedding model for embedding French sentences. So online, if you check for word embedding and French, basically, I mean, this is quite simple. If you want, you can find big tables. And for each row of the table, you have one word. And then you have a you have a vector of numbers for each word. So you can download these tables for English, for French, and for a number of other languages. It's quite easy to find online. I can provide you with some resources later on. Now, how you compute the word embeddings, this is another story. You can get them with a deep neural network, and there are other mathematical approaches to compute them. But these word embeddings, they rely on the patterns of co-occurrences between words. The fact that some words, they tend to appear together more frequently than other patterns. And by looking at this, you can create this word embedding. But it takes a bit of time to explain. And now I would like to move to the second section. So I will come back to that, and I can share with you word embedding, maybe not models, but at least the data sets. And we will do actually simple computations with word embedding, and you will see how it works. Actually, I have this in store for lecture number, I think number 6, something like that. So I will tell you more about this then. Okay. All right. So do you have any question apart from word embeddings? Is there anything before I move to the next part? Or are we good? Oh, no, this one is the activities. This one is the one I want. Are we okay? All right. Yeah, I don't see any question. I'm going to assume it was clear enough. And then I will move to the next part. Okay. Thanks, Mohsen. So the first lecture I would like to have with you is on something that in a way would be the first step of natural language processing and text mining if you play with text. So when you want to analyze text, there might be mistakes in what is written. And mistakes like this is little bit, I mean, it's like noise. If you have a data set and you want to apply some data science techniques. So maybe you could say that the first step when you want to do text mining is to correct errors, if there are some. If you process news articles, for instance, you might expect that actually the errors were corrected before and actually the text are quite error-free. But now if you want to deal with stuff that everyday people have written, you might have more errors and you may want to correct them. But actually what I want to share with you today goes way beyond that, is how we create tools which help people to create documents without errors. So the stuff like autocorrection on your phone, spell checkers, what you have on Word or on other software, and beyond that. So that's what I'm going to cover today. It's not machine learning oriented, but there is some algorithmics in it, which I can illustrate and introduce, and I will tell you a little bit about deep learning as well, what you may do. So this is about these questions. How does your phone or your text processor detect language mistakes? How does it detect them first? And then how does it possibly suggest corrections? And we can also wonder what is easier to detect and correct and what is more difficult. So I would like to try to answer these questions so that you understand how the systems work. And we all use these systems every day, okay? That's part of natural language processing, but that's like, let's say, a rather preliminary stage when you try to process errors, at least when it comes to text. So I just give you 3 examples. I bought some tomatoes for dinner. You can see the problem, right? The word in purple, of course. The 3 little dog barked at his arrival rather than dogs. And then the last one, yesterday, I fall on the ground. And here, of course, should be I fell on the ground. So here you have some misspelling. You have some agreement issues, like it's a plural and you did not add the S to dogs. And then yesterday, that suggests it's the past, but then you use the present tense for the verb, fall rather than fell. These are possible mistakes. And I could come up with yet other examples, and we will all agree. I mean, I hope it's quite intuitively quite clear that we can make a lot of different types of mistakes. The point is that to address these mistakes, you may not need to really understand the sentence, or you may actually need to understand more or less the content of the sentence in order to provide a meaningful correction. Some errors are what I would call lexical, but some are more syntactic, grammatical. They have to do with the grammar of the language, like English or French or Kinyarwanda or Farsi. And some errors are more semantic. So some of these errors are going to be simpler to address and others will be more challenging. That's what we're going to see. So at the end of the lecture, hopefully you will be able, in terms of intended learning outcomes, explain why autocorrection and spell checking are important. I mean, that should be quite clear, I guess. Explain the different types of errors that we make as users and the challenges they create for computers. You will be able to describe and apply some basic algorithms used in spell checking. I'm going to give you two very well-known things. And then you will be able to explain to some extent more advanced approaches relying on deep learning. So that's what we have in store for today. And that's the plan. I will introduce text data and errors. I will tell you about the different types of errors, a typology of errors. Then I will introduce what we call skeleton keys, and we can play with that a little bit. Then I will tell you how you can compute the orthographic distance between two words. I will skip part 5, but you can check later on. And if you have questions, you can ask me. It's just how you can move even further. And I will tell you a little bit about deep learning approaches. So that's what we have in store. The take-home message is, I want to tell you that spell checking, that's a basic case of natural language processing, but basic doesn't mean it's simple. Because actually, in a given context, you may have many seemingly acceptable forms, and you need the machine to sort out the different options. And that's not easy. It's not easy to correct mistakes. You have people who are expert in that, right? If you work in a publishing house, you will have people who are in a newspaper, you will have people who will be expert at reading stuff and quickly pointing out the mistakes that were made. If you consider classical approaches, that means without deep learning, you can get reasonable performances if you check the orthography. But if you want to deal with the grammar, like what we call grammatical spell checking, we will see that it's much harder. Deep learning approaches, they offer maybe the opportunity to get better because they can check stuff at the level of the sentence, relying on statistics and statistical patterns of how words they appear with each other. It won't be perfect, but it may be better. And what we should keep in mind also is that different languages will raise different challenges. If you play with French, which has quite a crazy, which has a huge number of crazy rules when it comes to writing, the fact that how the word is pronounced and the word is written is not like a one-to-one correspondence, that makes it very tricky when you play with French. English is a little bit better, but not that good. But there are languages which are way more transparent, like Serbian, for instance, the language spoken in Serbia and in a few other countries. Now think also if you write Chinese, like people here in Hong Kong and in China, processing Chinese characters is kind of a quite different thing from playing with letters and alphabets. So different languages, different challenges, quite obviously. And you may try to tailor the methods to the target language or languages you have that you need to work with. So these are the takeaway points in a way. Now that I'm done with that, let me introduce text data and errors, broadly speaking. First, I want to tell you I'm going to skip something. I'm going to skip character recognition because actually this is more about computer vision than language processing. You have text as an image, text made of pixels in a way. Then you can apply character recognition to extract the letters and the words and the sentences from the pixels. And when you do that, you will have specific types of errors in the process. And they will appear with specific frequency of occurrence, and you may have tailored approaches to that. So you have something, for instance, that we call ligatures in a number of written scripts. When you write Arabic, for instance, I'm not sure if some of you can write in Arabic, but yeah, I guess some of you, yeah, I think so, maybe. Then when you put all the letters together, you bind them together. And you need to pay attention to that. Or if you check the final word, writer, you will see on my example here that this may appear in some scripts as something like this. So you see the letters, they become combined. And that's what we call a ligature. Or sometimes when you have two F, one after the other, you may have something like the F, the upper part becomes merged or something like that. You have a number of things like that. That may create difficulties for the system. But if you are aware of these possible difficulties, you may know how to address them. So I just want to mention that, but I'm not going to spend time on that. Why is spell checking and autocorrection important? We could say very simply because of the amount of text we produce and which are around us. A few years ago, email, every day, 269 billion emails sent and received on a daily basis. 269 billion emails per day on our planet. That's quite a lot of text, even if some emails are shorter than others. SMS, 2015, 6 trillion messages per year. You divide and you come to the point that it's around 200,000 messages sent per second. That's quite a lot of text. I'm not sure if you are using WhatsApp in Rwanda or in neighboring countries, but in 2015, you had around 14.4 trillion text messages per year. And you can be sure it's way more today. Web pages, 2015, so that's more today, obviously, but it changes a lot. It's difficult to know exactly how many web pages there are. But the Google index 6-7 years ago contained already around 45 to 50 billion pages. So that should be convincing enough when I tell you that there are a lot of text around us and they contain errors, of course. So why errors are a problem? If you write a report, if you write an essay, you want to produce a document which is free of misunderstanding, which looks nice. So first you want to avoid misunderstanding. If you make errors, that may create confusion, and that's not a good thing. If I give you a manual about how a nuclear plant works, because you are going to be employed in a nuclear plant, you don't want to read a manual full of mistakes. That is going to be distracting, and you don't want to be distracted when you learn how a nuclear plant works. Also, there is a strong social norm of good quality language. If you write very, very poorly in a number of societies, that will look, let's say, bad. That will create trouble for you. You may not pay too much attention about social norms, and if you write to your friends on social media, quite often you don't care about these things that much. But in professional context, that matters quite a lot. You'd better write well. And in some contexts, additionally, confusion can be even greater. So, for instance, we may consider machine translation. I have written 3 sentences in French. At that time, I did it myself, and then I checked the translation in English provided by Google Translate. There were some warnings, but still, this is what I got. The first sentence in French is correct. The typhoon destroyed a large number of boats. But then if you check the second sentence, and if you read and speak French, that would be obvious, you can see that bateau is misspelled. And that's the same thing for the third sentence. And then you don't know how the system does it, but then it translates bateau as battles first, and then bateau as bats, the animal. So of course, if you make a small typing error, then the translation is going to sound very, very weird. And this has to do with the fact that in French, the sound O may be written in at least 6 different ways, right? O, AU, EAU, and then if you consider the plural form, Then you can have also AUX, EAUX. So you have all these options, and this creates some opportunities for errors, let's say. But there are many other ways you can write in a wrong manner in a way. So these errors are a problem to some good extent. It's also a problem when you search for information. Let's say you've heard about this new singer, not so new today, but okay. You've heard about Rihanna. It's a singer. And you don't know how you should write her name. And actually, if you write her name wrongly, if you write Rihanna like RHIANNA, if you write like this, you will actually get 23 million pages returned by Google. And the first one will take you to someone named Rihanna. And she's a singer, but actually it's not the singer that is the most famous today. This singer with nearly 200 million results on Google. It's another singer. And then the confusion has appeared. You can write Rihanna in many different ways, and you will always get a number of results on Google. So you should write it the correct way if you want to get access to the correct information, to put it in a nutshell. So in order to address all these errors, you have different tools that have been developed. You have what is called autocorrection. And here, you don't need to do anything, no user intervention. The system will automatically correct what you write. And it may warn you or it may not warn you. That's the first thing you may think of. You may also have systems which highlight possible or likely errors. What you could see in Word, for instance, so a number of word processors do that. And then you may have suggestions of meaningful alternatives, meaningful corrections, but not autocorrect. But you will be told, hey, maybe that's this what you meant, not that what you wrote. So in search engines, for instance, in word processors, you might get suggestions like this. Under the surface, for these three different options, is the same approach. This is spell checking, checking the orthography, how the word is written. So this is what we can focus on, how to do spell checking. And then you can choose which approach you prefer as a user in a way. But from the engineering point of view, the real challenge is how you do spell checking well enough and as quickly as possible, of course. I guess you know these kind of things, embarrassing situations with autocorrection. So you are writing to your dad, happy birthday, dear Papa, or something like that. And then I don't know what you do, and then autocorrect write happy birthday, dead Papa. Then it depends whether your father has humor or not. And well, you can see these two examples. Or you want to write Coke, and then the autocorrection write cocaine or something like that. If it's with your friends, no big deal. If it's with your boss, it can be a problem, right? It can become embarrassing. So this may not be the most important, but you need to be careful with autocorrection, right? So you want your autocorrection system to be good enough to prevent embarrassing situations like this one. This is an example of highlighting some problems. That's Microsoft Word 2016. So not the latest version, but if you write, I will have to go to the office early tomorrow, and you write office with a single F, then it will tell you, oh, I detect something wrong here. And it's in red. And then you also have blue. I'm sure you know that. You should better behave in public, and you write in public with an uppercase I. Then you see this blue line under it. And that means there is some, it's not a lexical errors. It's more like a grammatical thing. You should not have uppercase here. And then you can see here, I wish I had not, should be eaten. And you wrote, eat all the chocolates. Then you don't see any red or any blue, which means the problem has remained undetected. So in some cases, you might argue that highlighting like this may be better than autocorrection, because then the user must do something. He or she must take active steps in solving the problem. And that means checking, for instance, possible suggestions by the word processor. And then if you can work with the help of the user, of course, the performances may be better in the end. Because some of the suggestions by the computer may actually be wrong, but the user may well be able to sort them out and then find the right option. So highlighting possible errors, that's a good thing. If you use Google and you type something, if you type it wrongly, you will see that actually Google will make some suggestions, and these suggestions, they include modifying the orthography. So that's something also I'm sure you have experienced. The question, once again, is how do we create the system powering this function? The system under the surface that does this, that proposes these suggestions. You see, if you would try on Google, I think it would still be the case today. You you want to type deep learning. And the first time you type DEWP, learning, and the second time you type like DEPT, like department in English, department deep depth learning, you will see that you will have different feedbacks. In the first case, you see that Google automatically modified, auto-corrected DEWP, turned it back into deep because that was the most likely, and it shows you the result. But then it tells you about that. I'm showing you results for this orthography. If you really want to look for what you type, then you should click here. That's one thing. It means the spell checker was confident enough that there was something wrong. But if you check DEPT learning, since DEPT is something you will find in English, and that's the abbreviation of department, that could mean something. Maybe you really want to find something like that. Learning at departmental level or something like that. Then it gives you the results. But then it also suggests, hey, did you mean actually something else? Like deep learning, because that's a term, that's an expression I get a lot from many, many users. So this is quite nice. Depending on the level of confidence of what you were looking for, the system reacts in different ways. And this has been tested to be effective for the users. So you may include that. You may take advantage of the degree of confidence that you may be able to compute with your system. So if I just summarize this, digital texts, they come in huge quantities and they contain errors. At some point, there are always a few errors. And you need to consider these errors to prevent confusion and to prevent misunderstanding in different contexts. Whether you are typing your essay on your computer or you are sending SMS or you're on WhatsApp or on WeChat or yet something else on I don't know what else you have, but yeah, Viber, etc., etc. Claude, that's a good question. Sir, can this autocorrection work during speech recognition? I ask this because a word may be pronounced differently. Yes, of course, you may have the same idea if you don't process text initially, but if you process speech. I would say this is a much harder task when it comes to speech recognition. Because when we say we pronounce the word differently, I mean, the acoustic space is continuous. It's not like a limited space like the different letters of the alphabet or something like that. If you consider French or English, you only have 26 letters, right? So, I mean, there are many ways to make errors, but I would say in terms of variation, in terms of different forms, it's more limited than what you have when you consider speech. So of course, you may also have, I mean, speech recognition. It's about trying to detect words which are pronounced differently. And I give you just one example. If I say the word, recognition, or if I say recognition, I have played with the duration, right? Fast, recognition, slow, recognition. You need now to build a system which can account for the time distortion between these two words. And it's okay now, we can do this well, rather well, but I mean, it's not trivial. And this outlines that as human beings, we are really, really good at this. Because even if you speak with someone who has a pronunciation different from yours, and you may have noise, and you have other people speaking around and everything, we are still very, very good at understanding what is being said. So we are really, really good at that, but it's harder to create good computational systems which do that than it is to create autocorrectors at the level of letters and words like text elements. But yes, of course, we can have that. Although you could say also that when we speak to each other, if you hear something that was mispronounced, you may not try to correct the person in front of you, right? You may just, you understand and then you move on. When you do something different is when you have your kids learning language. Okay, I have my son, 3.5, and he pronounces words in fun ways from time to time, like all children, right? All young kids. Then I will detect the mispronunciation and I will tell him or her. Another nice example, you have software which do that. You learn Chinese. When you learn Chinese, something that is very difficult, although if you speak African languages with tones, that may be easier. But if you are a French speaker and you learn Chinese, you need to learn tones, right? Ma, 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 like the 4 tones in Mandarin. In African languages, you have many languages which have tones as well, but they may have, let's say, only high and low, or they might not have, I mean, they have different kinds of tones. It depends, right? So when you learn Chinese, you can have software that will pay attention to how you produce the tones. You will have software that will pay attention to how you produce the tones. They will detect mispronunciation and they will tell you about that so that you can gradually improve. So yeah, I mean, that these different elements, hopefully they answer your question, Claude. So that's, of course, that's an issue as well at the level of speech. Do you have any question right now? I will do the second part and then we will take a break. Anything, don't worry, please ask me and I'll try to answer. Otherwise, then I'll move to part 2 and then we'll have the first break. Good enough? All right, okay. You can make a relevant distinction between 2 things, lexical spelling and grammatical spelling. When it comes to the first one, the former lexical spelling, this is something where you consider the writing of a word form, without considering its relationships with the other elements of a sentence. That's kind of the intrinsic spelling. You check the word as it should be written, but regardless of the fact that it should appear not by itself, but in a sentence with other words around. So just to give you some examples, you want to write invention and you drop the first N, and now you have something which is not a correct word, which is invention, sorry. Or you want to write orthography, but you drop the H, and then you have orthography. That would be okay in French, let's say the orthography, but in English it doesn't work, right? Or you want to have diffusion, 2F, but you only write a single F. That you could consider as issues with lexical spelling. So that's different from grammatical spelling. When you have grammatical spelling, you consider the organization of the words one after the other, connected to each other in the sentence. In linguistics, but you can forget about that, we have a name for this. We call it the syntagmatic organization. That's the organization in the sentence, one word after the other. And you have these words and they have relationships between them. So grammatical spelling accounts for that. So you could call it contextual spelling, is spelling in context. So that's when you check for stuff like grammatical agreement in person, in number, in gender, etc., etc. If you have something like this person has a dog, there is an issue, right? There is a problem in number agreement. This is plural, person and has are singular. Something doesn't work here, right? It's not that this doesn't exist. It's not that has or person are not acceptable words. But when they are put together in a sentence, we can all see very clearly that there is a problem. So that's one problem. I mean, that's where grammatical spelling comes into play. Or if you speak French, you know that you have the verb avoir, to have, third person singular. He has a dog. Il a un chien. A, you write a. But if you say, he comes to the swimming pool, il vient à la piscine, then it's a with the accent. So if you write il a un chien with the accent, or il vient à la piscine without accent, now you have a problem. And this is a grammatical issue. It's not only lexical spelling, it's an issue of grammatical spelling. Then, of course, you have the conjugation of the verbs, which are quite crazy in French, much simpler in English in this case. So all these things, they relate to grammatical spelling. So this is an important distinction. As a consequence, you have what we call lexical spell checkers and grammatical spell checkers. So orthographic spell checkers or lexical spell checkers, what they do is they take words and they compare their forms to orthographic models. And if you can find a model for a word in a text, then you can accept the word as valid. But if you have in the text something like if I mention, you may not be, I mean, you won't find a model for this because this is not a proper word in English. Then the spell checker will detect there's something wrong and it will propose a plausible correction. So you have software which do that. A-Spell, I-Spell, they are autonomous pieces of software, but usually you find them in word processors or in web browsers or in mailers like Outlook, like Firefox and Google Chrome and all these things, and Word and yet others. So this is orthographic spell checking, and you can perform it online. And what I mean by online is you don't have to wait until the end of the sentence because you don't need the other words. It's not grammatical spell checking. So online means as the text is being entered, the I mention of deep learning, blah, 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 blah. When you write invention, the computer, the system can very quickly check if it knows this form. And if that's not the case, then the warning can pop up. And usually you highlight the errors to warn the user. You may underline them, you may use color, etc., etc. So that's orthographic spell checking, lexical spell checking in a way. And then you have grammatical spell checking. And then that's more difficult. You need to check that the words in the sentence, in a sentence, they conform to the rules of the language. Is your sentence correct? Not only the shapes of the words, but all these words together. Do you have the correct agreements in tense, in number, in gender? Do you write the moon in French, la lune or le lune? And if you write le lune, of course, it doesn't work, right? Because the word moon in French is feminine, etc., etc. So grammatical spell checking needs to account for the rules of the language, not only the shapes of the words in isolation. So you have some grammatical spell checkers today, some software you can find, and they will be at least in part sensitive to the context of the sentence. They can tell you, for instance, they can warn you of lexical forms that can be confused because their orthography is quite the same, or maybe because they are commonly confused. Let's say that in English you write disinterested, and the system will have the knowledge that people often confuse disinterested and uninterested. And then it may give you a warning about that so that you double check. When you want to do grammatical spell checking, this is much harder than orthographic spell checking because you do not only need like a dictionary of the words, you need a model of the whole language, a model of the grammar of the language, and that is way, way more complex. So different types of errors, some are much easier to address than others, basically. If you are in a place like, I think in Rwanda, that should be the case. Although English is now more prominent than French, unless I'm mistaken, but I'm quite sure of that. You may still, in your daily life, in your work, you may use your computer partly in French and partly in English. Am I right to say that? For those of you who are from Rwanda, do you write both in French and in English? Are there some people like this? For me, I am French. I work in Hong Kong. I will send emails to my colleagues in France. I will write in French most of the time. I write to my colleagues here for anything related to this university. I have to write in English. So when I open a Word document, Word doesn't know if I'm starting in French or in English at first. So if you are in a multilingual context, and you could think of other languages than French and English, obviously, right? Then if you start to type, the computer must first detect the language that you are using. And sometimes you write in English mostly, but then you want to quote a passage in French. So you are switching within the same document from one language to the other. It can happen in some circumstances. The point is that here, you may have something which is an error in the language, but not an error in another language. And we have this in French and English quite a lot. Exemple in French with I. Example in English with A. Aventure in French. Adventure in English with a D. No D in French. And many words like that, corresponding words like that. So if the system believes you are writing in French, but actually you are writing in English, you write example like you should write it in French, and the system doesn't detect that actually you are making a mistake because actually you are writing in English. Or that's a little bit subtler. you have American English versus British English. And usually you want your text to fall into one category or the other. You want to write only in American English or only in British English. Maybe you should not mix the two. Color, color. Do you use a U or not? There are many, many words that spell a bit differently, whether you write in American English or in British English. You want the system also to be able to detect that. It's not exactly two languages, but it's kind of the same, right? So usually when you write, like in Word, the system will eventually detect the language you use, but it will take a bit of time. So sometimes no problem. But in some circumstances, some users, they will use different languages. That's yet another preliminary challenge for the system. When you consider French, English, German, maybe Arabic, Chinese, you have a lot of resources. But if you consider smaller languages, and what I mean by small is less speakers and less resources, less computational resources, it becomes even harder to build the systems. So there are some languages for which we don't have as good systems than for others, as for others. These are different sentences that are entered in the past in Microsoft Word 2016. And you could find that you're not going to work today, or Office with 3F, or I ate dinner with my friends tonight. He ate dinner with his friends yesterday night. That works. The problem is detected. But now if I write Julia ate dinner with her friends yesterday night, now the error remains undetected. And it's a bit weird because this sentence is not very different from the two above, right? In one case, I use I. In this case, I use he. And now I'm just using a proper name, Julia. But the rest of the sentence is very similar. But here, the problem appears, the problem is detected, and not here. And the other things, this is not his cat. The problem here, the agreement, undetected. I was late. Maybe I was latte, the drink, undetected. You was not sure you would come, which is quite a big error, actually, undetected. So what you can see here, this error is orthographic. It's a lexical issue. That's okay, detected. All these errors, they are grammatical errors. This word exists. This word exists as well. These words, all these words exist. It's when you put them together that it doesn't work. But you can see that Microsoft Word, for instance, will try to do some grammatical checking, but it doesn't work so well. That's the conclusion I think we can draw from these examples. There is some level of grammatical spelling, but it's not very, very strong. That's when you see stuff in blue most of the time. Something else that is quite important is that when you make errors, there are different types of errors. And in particular, there are errors of performance and there are errors of competence. So if you want to do orthographic spell checking, you have different methods. And these methods, they will target different types of errors. Most of the time, you do the first kind, errors of performance. This corresponds to when you make a mistake. Actually, you know how to write the word, but you made a mistake when typing it in particular. So you know dictionary, but when you type dictionary too quickly, you drop the C and now you have dictionary and it's incorrect. But you know how it should be written. The errors of competence are different and they are usually more difficult to address because that's the case when you don't know how to write the correct spelling. Of course, when you type something, the computer doesn't know what is going on in your mind. So it doesn't know if you know the word or not. But usually when you don't know how to write the word, the errors you're going to make are going to be trickier, harder to solve for the system. So you will write 40 instead of 40, weather instead of weather. And these kind of errors are trickier than dictionary on the left. But once again, the computer doesn't know if you know the word. But if you know, the errors are usually not as serious as when you don't know the correct spelling. Okay, I'm nearly done, so we are nearly having a break. When you check this performance error, there are 5 different types, quite easy to understand. They are insertions. You add a letter which should not be here, dictionary, or you drop a letter, you do a deletion, dictionary instead of dictionary, or you duplicate a letter, like dictionary with 2 N. And that's a case of insertion, actually. You insert a letter, it's just that this letter is the same as the letter next to it. Or you replace a letter by another one. Dictionary, but you replace the C with a K, and you get dictionary with a K. Or finally, you have inversion, and instead of writing dictionary, you write dictionary or something like that. And actually, an inversion is kind of an insertion and a deletion. You may consider it like this. You type very fast, and you type one letter before the one that should come just after. You invert 2 letters. Yeah, just when you do that, when you have these performance errors, most of the time, which is nice, you don't make too many of them. Usually there is a single error per word. And if you assume this to be the case, it can help you to make suggestions. So I'm going to say it slightly differently. Orthographic spell checkers, usually, quite often, they are built with the idea, with the assumption that when you write a word incorrectly, you only make 1 error. Not 2, not 3, not 5, just 1. And they will use this assumption to find how you should correct the problem. So this is to keep in mind. So if I summarize this section briefly, there are different types of errors. Some are more common than others, and some are easier to address than others. Errors of performance, and especially when you make a single error in the word form, and orthographic / lexical errors. This is easier, and we will focus on that later on. All right. Is it clear enough? Am I too fast? Not too fast. Are you okay? Are you learning stuff that you didn't know before? Is it interesting? Let me know, because I don't see you, so I cannot read your faces and see if it's okay or not. Good? Okay, Jean-Claude is happy, so I'm happy. Okay. All right. Please let me know if there is anything you don't understand, okay? Because I can try to re-explain. So that's the introduction. Let's take a 5-minute break, and then we will start to think a little bit more in terms of techniques. Okay? We will do a bit of algorithmics. And yeah, so that's what will come. Okay, good. Okay, I'm glad to see that. Perfect. So let me drink some water. Let me just rest for a few minutes, 5 minutes, so you can also rest. And then I will introduce this skeleton keys. You will learn how to create that. Not very difficult, but quite interesting. So see you in 5 minutes. All right. I think we can resume. That should be around 5 minutes, right? Okay, so, okay, I can see this, the thumb up. Okay. So I've told you until now we have been more introductory, right, in what we've said. But how can we create? What kind of algorithm? What kind of ideas can we come up with to do this spell checking? What kind of methods have been proposed? Of course, there are quite complex things which are available today. I'm going to stick to the simpler things, which came first, of course, but they are interesting and they will give you a feel of what can be done. And the first thing we may consider are skeleton keys. So let's investigate a simple method to deal with performance errors. That's what we're going to do. The basic principle, I mean, is not very difficult, and I mean, you could guess it by yourself, no problem. What we have in Word and in all this software doing orthographic lexical spell checking is a reference dictionary. And this dictionary, it contains all the acceptable forms. That means the singular form of a noun, but also the plural form, and all the conjugations of a verb. But all the acceptable forms are in the reference dictionary. And now it's quite simple. You have a target form and you want to check whether it's something acceptable, lexically speaking. Then you check if this target form belongs to the dictionary. And if that's not the case, then there is a problem. Then you have a misspelling. And then you can issue a warning to the user, or you can propose a plausible correct form, or maybe several of them. Okay, so we have our dictionary, and we want to check if our target form is in the dictionary. The question, which is more practical, is how can we compare a target form to the forms contained in the reference dictionary? Let's assume that our dictionary is like the dictionaries we are all used to. It is alphabetically sorted. So we start with the letter A and then B and then C, and everything is how it should be. But you can see here on the right, you have iteration, iterations, the plural form, iterative, iteratively, iterators, etc., etc. So it's not like the dictionary you are used to, where you only have, let's say, the alphabet, the dictionary form of the words. Here we also have the plural forms and stuff you wouldn't find in the normal dictionary. So the system, let's say that the system checks where the target form should be located. So itinerary, you have this target form, and then you go in the dictionary, you go to ITI, you go as close as possible, and then you find that the words alphabetically that should come just before this word is itineraries. And the word that should come just after, so that's just before, and the word that comes just after in the dictionary is itinerary, like this. So that should be the one just before, that should be the one just after, and this one can't be found in between. Then you can say, oh, there is a problem here. And maybe what you can do is you look at the form just before and the form just after, and that may suggest reasonable corrections. Because indeed, when you have a word like this, maybe what you wanted to write is itinerary with a single R, and you made a duplication, and then you may suggest itinerary. If I take this example, this method seems to work quite well. But is it always that simple? I would argue, no, it's not always that simple. The list of words I'm just showing you here, this is called Milling-Strong's list, and I'm quite sure you can find it easily online. It's just a big table of word forms. Easy to download, doesn't actually take much space. The problem with my previous example is that if you rely only on the alphabetic order, you are bound to make mistakes. It doesn't work like this. It works only in some specific cases. Let's say that, for instance, you wanted to write literature, but when you type very quickly, you did not type the L, and you wrote literature instead. So if you go back to your list of words, sorted out alphabetically, and you find the word that should be just before yours, just before the target form, and the word just after it, you will find iterators and itinerant. Are these plausible? You can say, okay, iterator doesn't exist. Okay, there's a problem. But are iterators and itinerant plausible corrections? Not really, right? Because the target word actually is literature. So it means that if you drop a letter closer to the front of the word, that will create problems. But actually, everywhere it drops, unless it's really close to the end, you are bound to be in a problematic situation. So what you should do actually is consider all the possible insertions, deletions, inversions, etc. And each time you should look if, when you consider this insertion or this deletion or this inversion, whether you can find a corresponding entry in the reference dictionary. The problem with that is that even if you assume a single error per word, I've told you about this before, there are way too many possibilities. If you have iterature, just if you consider a possible insertion in the first place, you have 26 possibilities. But then the insertion could actually be in second place or third place or fourth place. And it could be a deletion, and it could be this, and it could be that. And you end up with dozens of thousands of possible options. You could still do it, but it's not efficient at all. It will take way too much time. That's why if we could come up with something a bit better, that would be very nice. So simple approach doesn't work so well. Can we come up with something a little bit more efficient? Not perfect, but better at least. So there is something which is called skeleton keys or alpha codes, and they were designed by two scholars in 1984, Pollock and Zamora. And this is actually how you take a word form and you turn it into an alpha code. And there is a recipe that you should follow, and it's not very difficult. First step, you remove all accents and diacritics. So if you check the word in French for elephant, which is éléphant, with actually two accents, I should have written like this. Maybe it would be better if I write like this. Let me. All right, it's here. Okay, better like this. So the first thing you need to do is to drop the accent. So you go to from elephant with two accents on the E, accent aigu, you go to elephant with no accent. Then if you have uppercase letters, you turn them into lowercase letters. That's the second step of the recipe. Then you sort letters alphabetically. And then you remove duplicates. So if you apply these four things one after the other, you go from elephant to a code, which is A, E, H, L, and P, T. So this is the skeleton key of the word elephant. The idea is that rather than comparing a target form to forms in a reference dictionary, like what we have tried to do just before, what you're going to do is you are going to take your target form, you are going to compute the skeleton key, and then you will compare the skeleton key to the skeleton keys of all the forms in your reference dictionary. So you don't compare the forms directly, but you compare their skeleton keys. Let's practice a little bit. I'm going to ask you something. All right. I would like you to compute the skeleton keys for 5 words in 5 different languages. And then once you are done, you can type them in the chat, and then we can see. So I would like you to find me the skeleton keys for apricot in English, délégué, which means to delegate in French, wahrscheinlich, which means probably in German, a quite interesting word with 1, 2, 3, 4, 5, 6 consonants in a row, Sturchlien, which means scratched in Serbian, and then a word that I won't dare to pronounce, which is a word in a language named Yupik, spoken very far in the north, and it means butterfly or moth. So I would like you to compute the skeleton keys for these different words using the recipe that is given here. So please do that, and please enter your suggestion in the chat. It's not very difficult, but just so that you can practice and see how it works. So I give you, let's say, 3-4 minutes to do that. So give me first the one for apricots in English. Okay, apricot, ACIOPRT. Do you agree with that? HP, there is a problem in your proposal, but I mean, it's just inattention, I think. Do you agree with ACIOPRT? We don't have accents, we don't have uppercase letters, so we just need to sort out the letters alphabetically, and then we drop the duplicates. So ACIOPRT, this is the correct order. And actually, we don't have duplicates here, so it makes good sense. What is the one for délégué then? Okay, M or MA, DEGLRU. Do you agree with that, everybody? Sounds good? So Chantal, when I see your proposal, I see that the letters, they are not alphabetically sorted. So there is something that is not okay. If we write the steps, we have délégué first. We are going to remove the accent. So it will become this one. HP, same problem. Your letters, they are not alphabetically sorted. If we sort the letters délégué in the right order, first we have D, then we have 3E, then we have G, then we have L, then we have R, and then we have U. If we now remove the duplicates, we have 3E. So we drop 2, then we get DEGLRU. Are you with me? Okay, I've just written the steps. Dropping the accents, ordering the letters, dropping the letters which are repeated. What about the German word? Full of letters Let's try this one. Wahrscheinlich. Wahrscheinlich. Okay, so these letters are in the right order. Okay, are we missing something? I think it's quite okay, I think. Do you agree with this suggestion? Okay, Jessie, Aimé, you seem to agree. So Chantal, you are doing something, but I'm not sure what you are doing. Oh, you did the next one, but maybe. Okay, so the next one, Storchlien. All right, okay. E, G, N, S, T. There is an R missing. Javandruma, Chantal, there is N, but there is also. All right. Okay, I will come back to this one. Okay, I think you are getting it now, everybody. And then the last one, the word in Yupik. So. So that's this one. Anyone for this one? All right, I think Jessie, you have it. Yeah. Okay. Not very difficult, right? I mean, once you get the hang of it is not very difficult. Is it difficult to write a small computer program in R that would do that? Can you write a program like this? Are you able, you would say, or would you be able to write a program that computes a skeleton key? Anyone? For those who are doing deep learning and stuff like that, it's quite different. But I would say if you can do deep learning, you should be able to okay, you don't. Okay, so I haven't the code for this one, but I will write the code. You are all doing R, I think. So I will write the code in R and I will share it with you, okay? So that you can see how it can be done in R, compute the skeleton key. So we found that apricot, he was something like, am I right? No. Okay, we had this one. What about apricot with a problem with two P's in the word? What would be the skeleton key of this word? It's the same, right? Okay, yeah, you guess right. You guess right. Hassan, the same, yeah. So you see that if you would check apricot with 2P and apricot with 1P, you would end up with the same skeleton key. And then we could try other words, like we could try the last one. What if we have this one? So that's the one, the last one on the slide. Is it the same skeleton key as the first one or not? Okay. So these two words, if you in UPIC, if you would compare them, you see that the letters, they are not ordered in the same way. But because you sort letters alphabetically, when you compute a skeleton key, you end up with the same skeleton key for the two forms. That's what I want you to guess. Apricot, you have two P's. for the second one. But because you remove duplicates when you compute the skeleton key, apricot with 2 P's will have the same skeleton key as apricot with 1 P. Does that make sense? It's a kind of gymnastics of the mind, right? If you do it for 10, 15 minutes, then it becomes automatic. But what I want you to have in mind here is that with these examples, we can see that some errors like reduplication or mixing the order of the letters, like inversion, that lead to the same skeleton key as the correct form. So that's related to this question. Why do skeleton keys work? Why are they interesting? This simple mechanism. So if I just rephrase what I've told you, skeleton keys, what they do is that they erase duplications and inversions. That's because we drop the duplicates when we compute the skeleton keys, and we also sort letters of the word alphabetically. So if letters are not in the right order, it doesn't matter. Even if the inversion, the letters which have been inverted, they are not one next to each other. It doesn't matter. They also erase diacritics, case, and deletion when the deleted letter is still in the erroneous form. So if you have twice the letters, the same letter in the first form, in the correct form, if you drop one of it, that won't be a problem. Which means that if you have a misspelled form, the skeleton key of this form will be the same as the skeleton key of the correct form. Just like apricot with 2 P, the skeleton key is the same as apricot with a single P. And then, if you compute the skeleton key of your form, and then you don't find this skeleton key in your dictionary, the skeleton keys of all the forms in your reference dictionary, they do not match the skeleton key of the target form. Then you may propose the correct form of the shared skeleton key. Let me try to take an example. In French, préférer, to prefer. On the right, this form is correct. This one is correct in French. But this one, if you write it like that, this is not the right accent, and you have one R too much here, too many here. However, if you compute the skeleton key of this word, you find this one. Now, if you check these forms in your reference dictionary, you won't find it. However, you will find forms which have the same skeleton key as your erroneous target form. What you could say then is that since these two words, they share the same skeleton key, maybe this word here could be the right form, the right correction for that word. Does that make sense? We check the form. If we find it, no problem. If we don't find it, we check the skeleton key and we check if some forms in the reference dictionary, they have the same skeleton key. If that's the case, these forms, maybe they are the right correction for the error that was made. Does that make sense? So we use this. Okay, we use the skeleton key to try to find plausible corrections. That's the idea. And because of the recipe of how to compute a skeleton key, this kind of makes sense. The forms you may propose, usually they are what you want. Not always, but that's quite what you want. Apricot with 2 P's, you don't find it in the reference dictionary, but if you compute the form, the skeleton key, this is the skeleton key of apricot with a single P. Then maybe apricot with a single P is the correction you want for apricot with 2 P's. That's the idea. It's not perfect because first, there are some errors which will lead to different skeleton keys from the one of the correct form. If you have rather than apricot, you write something like haricot. So you forget the P. Now, the skeleton key is going to be different from the skeleton key of apricot. So you won't be able, the system won't be able to suggest apricot as the correct form. So there are some errors which are fine because of the recipe to compute the skeleton key, and there are other errors which are not okay. Insertion of a character which is not already in the form, or deletion of a non-duplicated character. Like if you add S to apricot, maybe somewhere, or if you drop P of apricot and then P doesn't appear elsewhere in apricot, it appears only once. Then that's a problem. The other problem also is that you have several correct forms which may have the same skeleton key. If you check the skeleton key for boat in English, that's A-B-O-T. If you check the form for abbot in the church, this is also A-B-O-T. So you have some possible confusion here. And quite often when you consider skeleton keys, you end up with quite a large number of plausible corrections. So let's say that in French, sorry, you enter this word is incorrect. You compute the skeleton key because you don't find it in the reference dictionary, and you end up with EFPR. But actually, in French, préférer, the infinitive form of the verb, or the adjective that is derived from it, préférer, or the feminine form of this adjective with an additional E, or the conjugated third person singular form of the verb, préfère, all these words, they would share the same skeleton key. So that's 4 plausible corrections for the one you have just written. Maybe it's already quite a lot. Maybe it's a bit too much. So it's not perfect. It's not bad, but it's not perfect. For sure, when you sort the letters alphabetically, you kind of address the problem of the alphabetically sorted reference dictionary. The example I took earlier of literature, you drop the final L, the first L, and then you don't know each literature. I mean, the place where it is in the reference dictionary, it is not meaningful because you dropped the first letter. So actually, if you use skeleton keys, that will be partly addressed. Because if you write the dictionary, or if you forget the first D and you write dictionary, the forms will both begin with A. It's still not the same. The forms are different, but they are quite close. And you don't need to bother with the alphabetical order, because the location of the transformation in the initial word form, the fact that you drop the first letter rather than the last one, it doesn't matter because of how you construct, how you compute the skeleton keys. Now let's say that we have something like dictionary, and we have this skeleton key. How can we consider insertion or deletion? How could we reconstruct the possibility that dictionary was the correct word? What you could do, you consider all the forms in the reference dictionary, which skeleton keys, they differ by one character only. Geoffrey, I'm not sure if you are asking a question or if you just unmuted by mistake, but since the connection is not very clear on your side, maybe you can type your question in the chat, because I can see on the right of my screen.
No, I'm not muted, Professor.
Okay. Okay. Sorry. Yeah, I'll try to address this, but okay. So what you can do, because we assume most of the time when we make a performance error, we have one character difference. So what we can try is to consider all the forms which differ only by one character. So if we have this skeleton key, ACINORTY, if we want to assume that the letter that has been deleted by mistake is B, then we need to consider this skeleton key. If we consider that the letter which has been deleted by mistake is D, then we need to insert D, and there is only one way to do that. Only one skeleton key. If we think it's E, then we have this one. Now, if we think that our form is wrong because a letter was added by mistake, we can try to do just the reverse process, and we try to delete the A letter. So we check this skeleton key, CINORTY, or maybe the C has been added by mistake. So we drop it and we check this form. Or maybe it's the I, and then we check this form, etc., etc. How many forms like this do we have? The same as the number of letters, 26. So if we check these 26 modified skeleton keys, we will find all the forms in the dictionary which are one deletion or one insertion away from our target form. Only 26. We don't need to consider the tens of thousands of options like what I had told you before. So that's pretty good. That's still many, many possibly related forms, but that at least much better than before. So using skeleton keys will really simplify the problem. So if I repeat once again, because I know it's a little bit more challenging, we have this wrong form here. We compute the skeleton key, and then we consider the 26 possible modifications, either by adding other letters or by dropping one of the letters of this skeleton key. Then we get 26 new skeleton keys, and then we can check all the corresponding forms, and these may be plausible corrections. That may be too many, but that's quite good. Not too bad, let's say. And that assumes that there was a single error in the word, a single insertion, a single deletion. If your error was something different, like a reduplication or like a wrong accent on the E, for instance, this you will get the skeleton key, the first one will be good enough. But for these errors, insertion and deletion, then you need to consider modified skeleton keys. That's how you can do it. With a bit of luck, you end up with only a few possibilities, and then you may suggest them as plausible corrections. Do you see my point? Do you see that basically the idea is to reduce the complexity of the lexical form by computing these skeleton keys, and then we can use them to try to find the plausible corrections for something that is not found in the reference dictionary, something like dictionary or invention. Does that make sense? Yes, for Florence? Is it yes for others as well? Understood, Jesse? Okay. Tell me if something isn't clear, okay? Because once again, I'm very far away and I don't see your face. So it's really hard to see if you are very puzzled or not. So it's a balance, it's a trade-off. If you use skeleton keys, the gain is that it's quite easy to find plausible correct forms for a form that is not okay. But there is the trade-off, is that very often you have too many of these forms, and some are clearly non-relevant. That's what can happen. So it's good, but it's not that good. I will give you a very interesting story, an interesting story. Some sort of PR, public relations mayhem. 20 years ago, around more than 20 years ago, you had Microsoft Word 2000 at that time. And then when you have the French version of Microsoft, if you would type anti-stress as a word, Word would propose a correction. And the correction was anti-Arab, anti-Arabs. And you can imagine that if you want to, if you type something about stress on your computer, and then the computer tells you that the solution for your stress issue is to be against Arabs or something like this, you can imagine that it doesn't look very good, right, for Microsoft. So that was a problem when that was found. The interesting question is how come when people were typing anti-stress, the suggestion would be anti-Arabs. If you know skeleton keys, that makes a lot of sense. If you type anti-stress, at that time, this word was not in the reference dictionary. So then at that time, they would compute, the system would compute the skeleton key. And the skeleton key of anti-stress is AEINRST. At that time, in the reference dictionary, you didn't have anti-stress, but you also did not have any form with the same skeleton key. So what would happen then? It happened that Microsoft would look for close skeleton keys to try to propose a correction. So actually one form which was very close is the one with an additional B. So ABEINRST. And that was one of the only ones. And what was the word form, the words? The word corresponding to this skeleton key? It was anti-Arabs. And that's why Microsoft Word would propose this word as a plausible correction. It has nothing to do with being pro or anti-Arabs or anything like that. No racial discrimination or anything. It was just a small technical, it was not a technical issue. It's just the way skeleton keys were used in this software. There was one character difference in the skeleton key and there were not many options. So that's the option that would come up and be proposed. So that's a nice illustration of the limitations of skeleton keys. If I come back to these examples, you will have all the corrections because I typed everything and you will get it. I want to just highlight something, is that when we say accents, for instance, or diacritics, in French, we have we have and that we have different kind of accents, right? So this is the letter E with different accents. And if you apply the recipe like you did, like we did, you drop these accents. But I gave you a word in Serbian. And in this word, you could see an S, and you could see an S with a reversed hat or something like that here. You could see this one. My wife is Serbian. If I tell her, oh, this is an S with a reversed hat, she will scold me. She will tell me, no, it is not that. It's a different letter. So it's not a letter with an accent. It's just a different letter. This letter is not pronounced C. This is a ch. And this one is a ch, slightly different. And this one is a sh, and this one is a j. So accents work if you consider skeleton keys in French, but you need to be careful in one specific language. Do you want to consider, I mean, is it an accent or is it actually a different letter? So you need to be careful.
Sir, Professor.
Yes, I hear you. Yeah.
Now, if now you want to pronounce E in Serbian language, so how do you pronounce it?
Okay. In Serbian, compared to French, things are very, very easy. You have 5 vowels: E, I, A, O, U. And the way you write is exactly like you pronounce it, and vice versa. You never have any multiple options like French. You have O, and then you can like the sound O. It can be written AU, it can be written O, it can be written EAU, right? As water in French, right? But in Serbian, if you hear O, it's always O. If you hear A, it's always A written with the letter A. They have additional consonants that we don't have in the French or English alphabet, but then otherwise the sounds and what you write is a strict one-to-one correspondence. It's very simple to write. That's because the language was transformed more than 100 years ago to make it simpler. Okay, let's say you consider an African language with 2 tones. Okay, so maybe that in your language you have this vowel and this vowel. This one may be a high A, so A, and this one may be A, is a low A, right? When you consider your skeleton keys, maybe you want to discard the tones, or maybe you want to keep them. I'm not sure what would be the best decision. But accents and tones and diacritics, it kind of depends on the language you consider. Okay? I don't know if some of you are using languages where you mark the tones like this. Would anyone, any of you have like any language where you would, when you write it, you write the tone like that? Do you know what I mean? For some of you, maybe. I'm not sure. It depends where you all come from. But since there are many tonal languages among the Bantu languages, maybe you would write the tones like this. Can you tell me? Or nobody knows this? Don't be shy. Just let me know. Anyone speaks a language where you would mark the tones like this, like a 2 tones, high and low? Maybe no, I'm not sure.
Maybe like in Swahili.
Yeah, I think in Swahili they have tones, right? I'm not so sure because it's a little bit blurry in my mind because it's not a linguistic area I know so well. I know that many languages have Swahili. Swahili, do they have tones in Swahili? I think maybe indeed they have. Yeah, I guess so, right?
Because in Swahili, like TH, they think thamani.
Yeah, okay. So that would, but do you write the tones when you write Swahili? I'm not sure when you write the language, or you have your own, maybe there is another alphabet for it. I'm not so sure.
Like if you want to say thamani, is TH.
Uh-huh. TH. So the H would mark, okay, yes, in Ethiopia, we have one alphabet for every sound. Okay, so it's one letter, one sound. But do you have the tones in addition, like things like that? Because it's a different thing, right? We do have different tones on words, but we don't write
South
them.
Africa, I think.
Okay, okay. I think Olivia just say, okay, we have the different tones in the language, but you don't write them in the current way. Just like in Japanese. People like the Tokyo dialect of Japanese, they have tones, but they don't write them when they write. In Swahili, I don't remember if there are tones, but Jesse, if you know, there are no tones. I'm just not familiar. I just know that for Bantu languages, you have many languages with 2 or 3 tones. And usually they are flat tones. They are not contour tones. So high and low, high, medium, and low. But in Sekani, you have, but Sekani, where is it spoken? Sekani. Okay, I will check more and I will tell you. Okay, I need to check. I need a little bit of time, and I can come back and tell you more. But it doesn't matter very much for what I want to share with you right now. It's just the point that you may slightly adapt the recipe to compute lexical, to compute the skeleton keys for different languages, if that makes sense or not. Something like that. Okay. And in Ethiopia, you have your own alphabet, right? Am I right to say that? He would say you wrote that you have an alphabet for every sound. It's a special alphabet, right? Yeah, I have it in my mind more or less. Yes, I remember that. Okay. All right. Maybe I show you another algorithms. Okay. So we are here. Oh, okay, no, not the activity, but this part, yes. Skeleton keys are one approach. It's interesting, it's quite old, it's not perfect. Actually, what I will show you is the idea is actually older than that, but it's maybe a little bit more interesting. Skeleton keys, they are one option to detect errors and offer plausible correction, but they are not perfect. Maybe we could ask ourselves a more general question. That is the question of the proximity or the distance between any 2 words without transforming their structure like what we did with skeleton keys. Like we sort the letters, we drop some letters. No, we want to keep the forms, the letters of these words in the right order, and we want to compute the distance between these words. How can we do that? So there is something very, very well known that's called the Levenshtein distance. It was proposed by someone named Levenshtein. He's a Russian, I think, mathematician. He's still alive. He's quite old now, right? Born in 1935. And this is also known as the edit distance. And that's the number of differences between 2 orthographic forms. And distance in the mathematical sense, if the distance between 2 elements is equal to 0, it means the 2 elements are the same. You have symmetry. The distance between x and y is the distance between y and x, the same. And the triangular inequality, the distance between x and y will always be smaller or equal to the distance between x and z, and plus the distance between z and y. If you have done some math, this is the mathematical properties of a distance. Don't worry too much about that, but that's how you write it. So how we compute that? In 1974, that's quite a long time ago, Wagner and Fischer, 2 persons, they proposed an algorithm to compute this Levenshtein distance between any 2 words. And with the Levenshtein distance, what you can do is that you have a target form and you don't find it in the reference dictionary. Then what you can do is compute the Levenshtein distance with other forms, and the closest forms, the form with the smallest Levenshtein distance, they may be suggested as plausible corrections. So that's something you can do. You don't find the form in the dictionary, you compute the distance between this form and many others, and then you propose plausible corrections, the forms which have a small distance to your target form. So I'm going to show you how to do it, and then you will try by yourself. How do you compute this distance? You need to give a cost to different errors. If you have chicken and chicken, you see that the difference is that there is a missing letter, right? The missing C. So this has a cost of 1. It's a deletion error. If you have the distance between chicken and chicken with 2K, then the distance is also 1. It's the cost of an insertion. If you have chicken and you have inverted the K and the C, then the distance is 2. And then if you have chicken and you have replaced the first C by an S, then the distance is also 1. So this is the edit distance, this Levenshtein distance for very simple errors. Deletion error, distance is 1. Insertion or duplication, distance is 1. Inversion, distance is 2. Replacement, distance is 1. So these are very simple cases. But what happens when it's slightly more complex than that? So you can define it a bit differently. You can say that the Levenshtein distance is the minimum number of insertions, deletions, and replacements to transform one form into another. So if there is no insertion, no deletion, no replacement, the two forms are the same, and then the distance is 0. If there is one insertion, then the distance will be 1. If there is one insertion and one deletion, then the distance will be 1 plus 1 equals 2. Okay, Jesse, you want me to explain which part? This part? Is it the previous slide or is it just here? Okay. When you compute, okay, maybe start like this. The cost for a deletion is going to be 1. The cost for an insertion or the duplication, and it's the same, is going to be 1. The score for the cost for a replacement, you replace one letter by another, is 1. And inversion, if you invert two letters, then basically it's 1 insertion plus 1 deletion, and the cost is 2. So basically what you do when you have two word forms, you check the number of insertions, the number of deletions, and each time you found one of them, you add the cost. The cost for deletion is 1. The cost for insertion is 1. The cost for replacement is 1. So the number of insertions, deletion, and replacement you will need, that will be equal to the distance. Inversion, the cost is 2, because it's like you drop one letter and you insert it somewhere else. So it's 1 deletion. Here could delete C and then insert it somewhere else. Or you could delete K and insert it before the C. And then that would be 2 elements. If you delete 2 letters, then it's the cost of deleting 1 letter plus the cost of deleting another letter. So that's 1 plus 1, that is 2. So it's the number of modifications you make to go from one form to the other. And it goes in both ways. The distance between X and Y is the distance between Y and X. So to go from one to form A to form B, okay, let's do like this. Let's say that I have apricot. It's difficult for me to write because I'm left-handed and I use the mouse with my right hand. So sorry for that. Okay. All right. Apricot if I drop, whoa. All right, I'll do it better now. All right. Okay, apricot. If I drop the P and if I drop the R, I will get this form, like icot or something like this. So there is one deletion, and then there is another deletion. The cost of the first deletion is 1, and the cost of the second deletion is 1. So my distance, maybe I want to write distance of Levenstein. I can write it like this. The distance will be equal to 2. Now, if I go the other direction, I start from icot. Then I need to insert a P and I need to insert an R. So the cost of 2 insertions, and each insertion costs me 1. So 1 plus 1 equals 2. So it goes in both directions. The distance between X and Y is the same as the distance between Y and X. Apricot and icot, or icot and apricot. In one case, I have 2 deletions to go from the apricot to icot. And in the other case, the opposite case, the reverse case, I need to add 2 letters, 2 insertions. I also get a distance equal to 2. So that's the Levenstein distance. Does that make better sense now, Jesse? Is it better now?
Yeah, thank you.
Okay. Okay, good. So there is an algorithm. So the one created by Wagner and Fischers. And we use a matrix. So you don't need to do, if we add white space, I like this question. If you add white space, then you don't have a single word, right? Then you have 2 words. Let me see. Let's say that you added a space by mistake. I guess that's not very common, but let's say that that should still be possible, right? I've never seen this case being discussed, to be honest. But I guess you could consider the space just as one additional letter or symbol, and maybe you could deal with it the same. I'm just not sure because it's the first time someone asked me this interesting question. The question that is the related question that is interesting here is that when you type and make errors, do you often make the error of adding a white space or dropping a white space? I guess it can happen, right? When we type. This is not discussed in the original approach, but I'm pretty sure you could consider the white space as just another character. And maybe you could compute the distance just having like a 27th letter in the alphabet or something. I think that should work. Because these are just symbols, right? The computer is just computing symbols and playing with them. So I guess that should work the same. How can we compute this distance? I'm going to show you the algorithm proposed by Wagner and Fischer in the 70s. What you do is you create a matrix, but you are not going to do linear algebra or anything. You are going to fill the matrix following a simple recipe. So let's say I want to compare a buffalo and buffet. And you see here, you have an A, and here you have an E, and you have a T here, but you have L and O. So the beginning of the words are the same. This is okay, this is the same. But here in the end, is not only an insertion or only a deletion or anything, right? It's more complex than that. So how do we compute the distance? We create this matrix. You enter one word vertically and one word horizontally. And then you have one column here additional where you enter 0, 1 for the first letter, 2 for the second letter, and here you go up to 6. And then for buffalo, you do the same, but it's horizontal this time, and you start with the 0 here. 1, 2, 3, 4, 5, 6, 7. So you create this matrix for your 2 words. And now we are going to fill the matrix step by step. How do we do that? We apply this recipe. we go row after row. And for each row, we go from the left to the right. So we are going to fill this one, then we will fill this one, then this one, then these ones, then these cells, and then we will be done when we complete this one. And to fill it, you compute for each cell. If you check this cell, you are going to look at this one, and this one. If you are filling this cell here, you will look at this one, and this one. If you check this one, to compute the value, you will look at the value here, and the value here. So to find the new value for the cell you are considering at some point, you take the minimum of 3 different values. The value of the cell just to the left, +1, the value of the cell above, +1, and then the value of the cell in the diagonal, either +1 or +0. +1 if the 2 letters for the row and the column of the cell are the same, 0. And if they are different, you will choose +1. So let's try. With the first cell we need to do is the one in red. We have B for the column and B for the row. We need to check the value here, +1. 1 + 1 = 2. Then for this cell above, we check the value, it's 1, and we add 1. 1 + 1 is 2. And then we check the value here, it's 0. And then the letters are the same. So we will add 0 + 0, and then we get 0. So we have 3 values, 0, 2, and 2. What is the smallest of these 3 values? It's 0. So we write 0. And then we can shift to the next cell. And we are going to do it again. Okay, now we fill the cell in red here. I'm going to change the color. Annotate. Okay, take this one. We check the value on the left, it's 0, and we add 1. So we get the value 1. We check the value above and we add 1. Then we get 3. We check the value in the diagonal. So that's this one. And then now we have B and U. These are different letters. So we add 1. 1 + 1 = 2. So we have 3 values, 1, 2, 3, and the smallest of these 3 values is 1. So we pick 1. And that gives us the value here. And then, of course, we move to this one. And like this, 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 until we reach the final one. Forget what is written here. It's a little bit more difficult. No need to spend time on that. Do you see how it goes? How you fill the matrix gradually? You fill row, cell after cell. When you are done here, you move there, and then you do it again and again and again. Always the same recipe until you reach the final cell. If you do that and you don't make any mistake, the value in the final cell, bottom right corner, that will be the Levenshtein distance. For sure, guaranteed. That's what Wagner and Fischer, they demonstrated in 1974. Here, in this case, for this example, you see that you have many zeros in the diagonal, but it's not always the case. You have the zeros basically here for one good reason, is because Buffalo and Buffet, they start with the same letters. That's why you have zeros. But if you start with something different words, you won't get these zeros, you will get something else. So it depends on the 2 words you are considering. Okay? So once you know that, once you have the finals, when you have filled the matrix, we won't do it right now, but actually there is a way to go backward from the final cell to the first cell and to identify all the transformations that are needed to go from the first word to the second one. And you can do that. It's the next part of the algorithm. But this is a way to compute the Levenstein distance. This is a small algorithm that you do, and then until you reach the end. So what I propose you to do for now, so I take a rest. So my voice can rest for a while. I'm going to give you this one. Wait, let me see. I don't make mistake. Opa. We have seen during the lecture, dictionary and dictionary. Okay, dictionary is the right form, and dictionary, you can see the problem, right? There is this K, there is this 2N. So I would like you to take these two, and I would like you to build the matrix for me. Okay, and Florence, I will re-explain the diagonal. For the value here, you look at the value here. Here is 1. If the letters corresponding to the row and column of your target cell, if these letters are the same, you will just take the value straight. If the letters are different, you will take this value and you will add +1. And that's how you will compute the value for this cell. And then you have the value for this cell, the cell on the left, the value for the cell above, the value for the cell in diagonal, and you take the minimum value of the 3. So that's what I wrote here. Is it better now, Florence? Okay, all right. So I'm going to leave this one here, and then I want you to try by yourself to compute. Let me try to make it smaller. Okay, so I don't, all right. So dictionary, I want you to apply the same recipe, building the same matrix, repeat the process. Okay, now you can see everything. So I'm going to give you some time. If I would be in the classroom, the winner, the first one to get it right would get something nice, but I'm online, so I cannot offer any reward. But try to build the matrix and give me the distance and give me the correct matrix. So it will take some minutes, so I'll let you do that. Is that clear for everybody? Give it a try. Okay. The more you practice, of course, it's like the skeleton key. The first time it takes some time, but then you start to get the logic, and then you would get faster and faster. No, the star is not included. Oh, okay. Because in linguistics, when you have a erroneous form, you can mark them with a star. That's something you do. That's a linguistic thing. So you forget about the star. But that's okay. Good point. As a linguist, I did not pay attention to the star. That's just to say, okay, this form does not exist. That's the meaning of the star. And I will just mute myself for a couple of seconds. Is it okay? Are you gradually filling the matrix?
Yes.
Takes a bit of time. I know. That's for sure. That's how it should look like in the first place. If I draw the matrix, it should be like this, or dictionary should be vertical and dictionary should be horizontal. Doesn't matter in the end, the same result, but that's how it can look like initially. And I will show you this.
Could you please bring back the other question for us
Oh, yeah,
to
sure.
be able to fill? Yeah.
This one? Yeah, okay, sure. Do we have a super fast student who has already found the distance? Is there anyone? Maybe not yet. I have written the 3 first values in the cells so that you can check if you are doing it right or not. It's 1, 1, 2, 3. Okay. Uniter said distance 3. Would you agree with that? I think that's the right answer. Dictionary, Ictionary. We are dropping the D. We are transforming the C into a K. And then we have one difference with an N, additional N. So totally there are 3 transformations. It's not too difficult in this case. Chantal, it's confusing. Okay. Do you want me to do the first cells with you so that it looks clearer? Like I do the 1, 1, 2, 3.
Yeah, that would be better, and explain how you
Sure.
are doing.
Sure. Okay, let me do that. So we want to do this one first, okay? The first cell. On the left, we have 1. We add 1. So the first value is 2 here. Above, we have 1. We need to add 1. So here, the value is a 2 as well. And then we have the one in diagonal, it's 0. We have D and we have I. These are 2 different letters. So we need to add +1. So here the value is 1 for this cell. And we need to choose the smallest value between 1, 2, and 2. So what do we choose? We choose 1. And that gives us the first cell. Then we are going to repeat the process once again. If we move to the cell, right to the next now, here above we have 2. We need to add 1. So here the number to consider will be 3. Here we have 1, and the number to consider will be 2 because 1 + 1. And here in diagonal, we have 1 already. And here we have I, and we also have I. The same elements, the same letter. So we need to add 1 + 0. So here the number to consider is 1. So we have 1, 2, 3. We pick the smallest number, which means we pick 1. And that gives us the new element. So 1, and then again 1. Now, if we look at the next one, here we have 1, we add +1, so the number here is 2. Above we have 3, we add 1, 3 + 1, the number is 4. In diagonal, we have 2, but now C and I are different letters, so we need to add 1. So the number 2 + 1 is 3. We pick up the smallest value between 2, 3, and 4, and the value we pick, of course, is 2. And then we can go on like this for a while. Does that make sense? Chantal, does that make sense with this step-by-step approach?
A bit. Let us try then.
It's always the same thing. You consider the 3 numbers, you add 1, or sometimes you add 0 if the letters are the same, and you have 3 numbers, you pick the smallest one. Again and again and again and again. Here you have 2 + 1, 3. 4 + 1, 5. Letters are different, 3 + 1, 4. So the minimum value between 3, 4, and 5, and that's 3. And then you continue. Here you have 3 + 1, 4, 5 + 1, 6. And then we have I and I, same letter. So we do 4 + 0, that's still 4. Minimum value between 4, 4, and 6, that's 4. And then we have one more cell. And then we can, of course, continue like this. One last time for Jean-Claude, okay? Here, next one, we have 4 on the left. 4 plus 1, 5. Above, we have 6. 6 plus 1, 7. Diagonal, we have 5. But here, our letters are O and I. They are different. They are not the same. So we need to add 1, and we have 6. So 5, 6, 7, smallest value is 5. And then we continue. The issue is when you were starting. So what was the problem initially? We had 1 plus 1, 2. Okay. So we are good. What I want you is to feel confident that you can arrive at the end, even if you don't have time to arrive at the end, because time flies, of course. Should I show you the result? What do you think? So that we don't spend too much time on it and you can try at home a little bit more. Once you get it, it's just a matter of time that you can repeat the process until you reach the final cell, which appears in green here. Okay, I think you should be able to repeat it. Plus, I'm going to give you something so that if you want to try, you will get the correct answer. Let me show you. So if you would continue like this, it takes a while. This is the matrix you would get. You would finally get a number 3 in the final cell. That would mean the distance between the two words, the Levenshtein distance, is equal to 3. You can actually interpret it, as I told you. There is the difference of D in dictionary, which does not appear in Ictionary. There is the C that is replaced by a K, and there is the N that is duplicated. So that's why actually you have a distance of 3. You have one insertion, one deletion, one inversion, one substitution of letter, and one duplication or insertion is the same. So that's why we have the score of 3. How would you do that with a computer? You could try later to do orthography and orthography and find and see. What I want to show you is this one. And I will upload this on the Google Drive as well. Do you know this environment? Do you use RStudio? Are you familiar with RStudio? If you use R, I would say it's likely that you know RStudio. Am I right to say that? Is it the one you are using? Yeah, it's very good. It's the standard, right? For R, I think most people use that. So I wrote actually the code in R to do exactly what I've told you to do. So this is a small function. You see, it takes word 1 and word 2, and it's called compute matrix. And then you can see that it does exactly what I've told you to do. It first defines a matrix. It starts to fill the matrix with it gives the names of the columns and the names of the rows. They are according to the letters of the words. Then you start to fill the first row and the first column. These are this part. And then gradually, I'm using a dynamic programming approach. Small, like I have 3 loops, 2 loops, one into the other. And I'm moving from the left to the right and from one row to the row below. and I am applying exactly the method I've told you. So you can see that the value I am going to put in the cell j, is the minimum of 3 values. Is the value mi minus 1. So that's on the left, plus 1. The value just above, plus 1. So that's the j minus 1. And then the value in the diagonal. And to find it, I check the value in the cell just above and to the left. So that's why I have I minus 1 and j minus 1. And then if the name of the column and the name of the row are not the same, so the 2 letters are different, then I add plus 1 to this value. And I repeat that, and in the end, I return the matrix. If I do that, up, and then I'm asking compute matrix up, what do I get? I get exactly the matrix that you should have if you apply it correctly. Okay, it's a simple algorithm to get the matrix. So now you can try with any 2 words you want, even more difficult ones, like more distant ones. Let's say I want to find the difference between elephant and gorilla. Why not? 2 animals. This time I get a distance of 8, which is much higher, right? Because the words are very different. So I will upload this small piece of code in the Google Drive, and then you can try to play with it. Okay, is just loops and filling the values of the matrix step by step. Does that make sense? Okay, in R, actually, usually you may have heard that in R, we try to avoid using loops because this is a more like a functional language, and we have functions like apply and stuff like that. So people would say, oh, you should not have loops. But for this simple example, loops are okay, let's say. So I will upload this, and you will be able to play with it a little bit more at home later on. Are we good? So this is a different approach from the skeleton keys, right? This time we compute distances between word forms. So if we have dictionary and dictionary and the distance is 3, then of course we will need to see if we have other word forms where the distance is less than 3. Because if we have other forms in the reference dictionary with a distance less than 3, that means there may be more plausible corrections than dictionary. But I think there are not other forms which are closer than dictionary, actually. So that suggests this is our answer, or the one very good plausible correction. Are you with me? Does that make sense, all of this? I'm just doing some algorithmics, simple algorithmics toward spell checking. Is it good? You need, if you want to get the hang of it, you just try at home a little bit more, okay? I know it takes time to fill the matrix, but if you do it 3-4 times, of course, you are going to feel it's easier, right? And it depends how good you are with this kind of mental processes, but okay. What I want to tell you is that that's one way to do it. Wagner and Fisher's algorithm. They are actually faster algorithms to reach the same result, but they are not so easy to explain. So for instance, in 1986, Myers and collaborators, they published another algorithm that is faster, where you don't have to do as many operations as this one. Also, you have slightly different distances. For instance, some people will consider an inversion to have a cost of 1 rather than 2. Or maybe you would like the substitution to have a cost of 2 rather than to have a cost of 1. And then you have what we call, for instance, the Damrow-Levenstein distance is slightly different. It's just the inversion has a cost of 1. And then you have also the Jacquard index or the Jacquard distance, the same. So you can have small variations around what I've shown you. Okay? Depends on what are your assumptions, I think, with respect to the words and the errors that are made. So that's what you could do. If you want to be a bit smarter, you could say that some letters are more likely to be replaced with some other letters than with others. Let's say that you can see that people usually, if they make a mistake, they will replace, let's say, B by D rather than by F. Something like this. Then you could account for that in the computation of your distance. Why is it meaningful to say that? Because you type, right? When you type on your keyboard, you are more likely to make mistakes with surrounding keys. Let's say you are typing, you want to type B and you type too fast. Maybe you will type a V, or maybe you will type an N, or maybe a G, right? Because these are the letters which are close to B. Or if you want to type O, maybe a plausible error is you type P instead, or I. So you could actually account for these kind of things to make your distance a better one. That would account for how people type on the keyboard and the way the letters are distributed on the keyboard. Do you know why we have this QWERTY keyboard in English and why do we have this AZERTY keyboard in French? Do you have any idea where it comes from, actually? Does anyone know about that? Why do we have this keyboard? How come these letters in this order, and why different languages have slightly different orders? Filling puzzles, filling number puzzle. No, I think is a different thing. And it depends the kind of puzzle you have in mind. It's not letters that usually follow each other. Nope. It actually comes from a very long time ago, well before the origin, the birth of computers. Yeah, Chantal, what do you think? What was the initial idea? It doesn't come from Latin. It doesn't come specifically from French or from English. It comes from before computers. I think it's hard to guess if you don't know. What did we use to type before computers? We used typing machine, right? Writing machine. At that time, with the writing machine, if you would type too fast, the letters, they would get stuck with each other. So people, they thought of a way to slow down the speed at which people could type. And they found that this organization of the letter for English would slow down speech, so that would prevent the letters of the typing machine to get jammed. So it's actually for you to type more slowly. And people got used to writing machine, of course. And when the first keyboards for computers appeared, people kept the same order because people were used to this order. Even if with a computer, you can type much faster without any problem of jamming or anything because it's digital. It's no longer like a typing machine. So actually this order comes from the past when you wanted people to type slower. Today it doesn't matter, but we have just kept the habit. If you look on the internet, you will find that some people, they have created keyboards actually to type faster on a computer. And the arrangement of the letters is different. But that's why we have these different things. And one language, the letters have different frequencies and they appear next to each other in different ways. So each language can have its own keyboard. That's where it comes from. But you can use the knowledge of the distribution of the letters on the keyboard in one language to make better systems for spell checking. That's something you can do to make things better. Does that make sense? So you can try. There are different variations. Okay. So you can compute this Levenshtein distance between any two orthographic forms or distances which are quite like the Levenshtein distance. You can do some adaptations here. If you have an erroneous target form, you compare it to many different existing forms to find plausible corrections. And because computers are so fast today, it's actually super fast to compute the matrix. So you can do it very, very fast, and you can then find plausible corrections. So that's likely what you will have in the background of some of the systems you are using, which will do autocorrection or spell checking. Does that make sense? Are you still with me? Yeah? All right.
Yes.
Okay. So if you want to read more by yourself, you can check a little bit more. So I tell you about the typing machine. It's here actually. So you see, if you check a standard Swedish keyboard, the letters will also be a bit different. That's normal. What you can have also is you can find online. I gave you the address here. You can have some data sets of errors commonly made by people. And then that can also be very helpful if you want to build your own spell checker. So for instance, you have the Birkbeck spelling error corpus. And if you find this, it's a text file, it's a big table. And you will find that people, Japanese people, when they write English, they tend to write 100 with an A, or colorful like a color with the U before. So you can see the type of errors that are commonly made. And you can use this knowledge rather than doing something else. And you have some examples like 300 people, it was colorful. So these are like situations in which these errors can appear. So either you build your system, or you may have something like a corpus of examples of errors. And then you may, rather than doing something non-supervised, you might think of having something like a deep neural network. And you may train the network with the erroneous form as inputs and the correct forms as outputs. And then the system, if you train it well with the right data set, then if you input erroneous form or even erroneous sentences, if things go well, then your system might be able to correct the errors. For that, you need the training set, right? What we have seen yesterday. It's supervised learning in terms of machine learning. But that's something you may think of, right? You may use deep learning with many, many, many examples, and you try to predict the correct answer, the correct sentence from an erroneous version of this sentence. Does that make sense? This is how you may try to do it. If you give me 5 minutes, I can show you the analogy with computer vision. Is it okay if we take 5 more minutes? Or are you so tired? Is it okay? 5 minutes, then I will need to stop anyway because I need to go home as well.
It's okay. We can take.
It's okay? Yeah. Okay.
It's okay.
I want to show you the analogy with computer vision because I've told you natural language processing and computer vision, they are quite related. So I want to show you that there is some sort of parallel which can be drawn with how we can correct noisy images. You see here, there are we have something that is called denoising. It's when you have something like the numbers that you can see on the first row, and you can see that I mean, it's not very clear, right? You have a lot of noise in terms of the color of the pixels. But what you would like to build is a system where you can take these damaged images and kind of clean them to get something smoother, something easier to read. So that's what we call denoising, the process of correcting noisy images. You have algorithms like that if you like to take pictures and process them with a Lightroom or a Photoshop or stuff like that. You have stuff like that. Something you can do to do that, something very common for denoising, is what we call autoencoders. It's a kind of neural network, and it's called autoencoder because what you will do, you will give the input and the output are the same. So same input, the output is the input. What you have, what is interesting with this system is that you start with a large input layer, and then gradually you decrease the size of the layers until you have a small layer in the middle of the network. It's kind of a bottleneck. And then you increase the size again until you reach the final layer. So there is the part on the left we call the encoder, and the part on the right we call the decoder. And the fact that you have this kind of compression in the middle of the network, you will have a kind of compressed representation of the input. And from this compressed representation, you can generate the output. So that's what we call an autoencoder. Autoencoder because the output is the same as the input, but the structure is like this. There is this bottleneck, this small layer in the middle. So what you can do in vision, you will use these convolutional layers I've told you before. So you will have these convolutional layers on the left to create a small representation, a compact representation of your image on the left. And then to go from the center of your network to the right, you will have the opposite of a convolution, which is a deconvolution. We don't need to enter into the details, just want to get the idea that it's just the opposite. So this is an autoencoder, but this is a convolutional autoencoder because you encode the first image, the input, with this convolutional layer, and then you deconvolute the whole stuff to get back to an image of the same size. So that's a possible structure. So what you can do actually, if you train the network, not exactly with the same thing, but with input that to which you add some noise, then you try to learn the reconstructed input from the noisy input. If you have enough examples of noisy images with the corresponding non-noisy images for the output, the network is going to learn a representation of the numbers in the middle. And it is going to do the trick. It will be able, after training, to take the very noisy images and turn them back into denoised images. So you feed it with, sometimes it's the same, exactly the same input as the output. Sometimes there is a bit of noise, or sometimes there is more noise. And you do this again and again and again, and you train the network. After a while, your network, you will give a noisy digit, and it will give you the denoised digit. That's what you can do. Of course, I go a little bit quick here, I know, so don't worry if it's a bit too fast. I just show you what you can do in computer vision. That's very common. You can also do very nice thing. You train the network with color pictures and black and white corresponding pictures. Input is a black and white, output is a colorful picture. You train the network with many different pictures. And after a while, you can give new pictures and it will add color automatically. So here you have a famous US president. You give a black and white image after training, yeah, and it will kind of color the picture given what he has learned about the colors of many different pictures. So neural networks, they can learn to do that. They can do it with videos as well. So that's how you can color old films, old movies, old pictures. What I want you to think of is that rather than having images, which can be noisy, we could have sentences correct, which are correct, and sentences we can add some noise, some errors, some grammatical or lexical errors. And we do the same as with computer vision, except that this time we deal with language rather than pixels. And that's how you may build a system that will do some denoising in linguistic terms, that is trying to correct errors in a text, in a document. So if you do that, you will not use convolutional layers. What you may use instead is recurrent layers. And here, actually, I won't enter into the details because we don't have time anymore, but the system will be a little bit like the systems which can do sentence-to-sentence translation, so machine translation, which is another part of NLP. So you can think, in a nutshell, you can think of deep neural techniques to try to do autocorrection. But what is nice is if you have many examples, the system will be able to grasp at least some of the grammatical errors, because it will have seen so many sentences with problems and without problems, that we will be able to pick it up, like what is going on in terms of what is a correct sentence at the grammatical level, how you have agreement, plural or singular, the gender, etc., or the fact that if you have yesterday in a sentence, maybe the verb should be past tense rather than present tense, and so on and so on and so on and so on. What is the application of computing the error distance? I think one application is really for spell checking. I think that's the main application. Now, if you do research, I could give you a research example of how I use this one to compare, for instance, the error distance, the orthographic distance, with the semantic distance between words. That's something I'm working on these days, actually. So, but spell checking, actually, this edit distance, you will also find it in other domains. It's not only for words. This is a very famous distance. So there are other domains of application which are not NLP, actually. Okay. I just want to add, there are no tones in Swahili. It's one of the few Bantu languages without tones. And then I just found this paper. I will put it in the Google Drive. Strategies for representing tone in African writing systems. And if you read this paper, I checked very quickly while you were doing the matrix. Some languages, like this one, Chung from Cameroon, they will mark all the tones, and some other languages, they won't mark the tones at all. Okay, so just to come back on what we had told you before. I will upload this. It doesn't really matter, but if you want, you can have a quick look. Depends what language you are speaking and how it works. All right. That's a lot of information, I know. Okay, I try to provide you with as much stuff, and because it's recorded, I just expect that if you want to really get to the bottom of things, you can just listen again and you can ask me questions and everything. Okay, but that's what I wanted to show you about spell checking and some strategies you can use. Skeleton keys, distance stuff, the Levenstein distance. And then I just wanted to outline what you can do with deep learning systems and how actually it resembles what people do in vision, in computer vision. The Google Drive, I will copy the address again. The address is here. Let me find it. Give me just 1 second. The address is here. So here you will find everything. Just give me a little bit of time to upload the stuff, but it's coming. Like after each session, I will upload stuff. Are we good for today? Is it okay?
It's okay.
All right. Would you share it on emails? All right. Yeah, I can send. I didn't. Okay, I can send an email to everybody with this one. Actually, I can do that. I will do it. I will do it now. Yeah, I think for today is quite a lot already. So I won't. I think now we all need to rest for a bit of time. Okay, I see your email. I think I have it in the list, but okay. Okay. If you find it interesting, then I have much more in store like this for you in the coming days. So, and also this one maybe is not the most applicable for you, but we will. Okay, you were not on the list, Isaac. Okay, so I'm going to send you the stuff. All right. If I hadn't you before, I'm copying your emails right now. Okay. So we will cover more stuff, and I will share some tools online also that you may use. Okay, I've copied your address, guys. So don't worry. Okay. I copied this one as well. Claude. Okay. So unless you have questions you would like to ask now, I can just say have a good day or have a good evening for my friend who is online with me now, who is in Hong Kong as well. And I will see you tomorrow, same time.
Hello, Professor.
Yeah. Any questions? Sorry.
So yeah, on the drive of Google, so there is only the PPT, there is no video.
Oh no, the video, they are because the videos are too large. So on the Google Drive, there is a Word file. If you check the Word file is named, let me say, okay, I share, if you see my screen right now, this is the content. There is recordings of the sessions, okay? So if you open this one, you will see the recording. So you need to click this one and then you will find the recording. And later today, I will add the second session as well. But it needs some time for the system here in the university to process everything. But later today for you, sorry, tonight for me, you will see I will add something and that will be today's lecture. Clear enough? Okay. Okay, and yes, somehow difficult. Yeah, I know sometimes it's a little bit difficult, but just take it one step at a time and just trying to get the main ideas. Maybe the small technical details is okay. It's not that much the key thing. If you get the general ideas so that later on, if you need, you can further by yourself, then I think is good already. Okay, Justin, I am taking your email as well. Okay, I copied it. Don't worry. I will send it to you right now. Okay, so I will stop sharing this and I wish you a good day and I will see you tomorrow. Bye-bye, everyone. Bye-bye for now.
Okay, thank you.
Bye. See you.
See you.
Thank you. Bye.
Bye-bye, Jessie. Bye-bye, Rose. À plus tard. Some French. Yes. Bonne journée. À demain.
À demain.
À demain.
À demain.
I'm sure there are many French speakers actually among you.
Hello, Professor.
Yes.
Generally, so for me, it is only the request on my side.
Yeah.
Where I will need to have a conversation with you just via the virtual, so that maybe I have an idea, so maybe I can share with you So I don't know when are you going to give me the time, or you arrange it then and we talk.
If that's okay with you, maybe it would be good to do it just after we are done with this, because actually every day, because here the situation with the COVID is very crazy. So my kids, I need to take care of my kids sometimes, and then I have the teaching 3 hours. So I'm really quite busy during the day. But then maybe we can meet online, no problem, but just after the seminar. Would that be okay? Are you in a hurry or not?
Yeah, it's fine. Yeah, after seminar.
Okay, then we do that. You send me an email in case I would forget, because yeah, I'm quite kind of very busy with everything that happens now. But then we can set up a time and then we can discuss. Yeah, that's okay, no problem.
Yeah, the curiosity question. So at the end of this session, are we going to get like a certificate?
That I need to check with the people running the center. I haven't planned anything, but if that would be something useful, maybe I can check whether something can be done. Yeah, maybe. If you think that would be
really,
useful for you.
Yeah, it will be useful because at least like you see the people who have registered, so that you see the names,
Yeah.
or you put the link then, so that at least you do a certificate at the end of it, so that this one to be useful, because now it is new here, like in Africa or in Rwanda.
Sure. Okay. So I need to kind of make sure of who is showing up every day then. So I need to kind of capture the lists of names and stuff like that. So okay.
Yeah.
Okay. I'm going to double check, but I think that should be possible. Yeah. Okay.
Yeah, sure.
Okay. No problem. Bye-bye for now. If there are no more questions now, I will maybe end the session then.